My name is Marco Flowers. I'm a fourth-year computer science major. I've been on the team for 4 years and have worked with UAS Technologies for the same amount of time. This year I was the project manager, and at competition I will be the safety pilot.
Hi, my name is Matthew Ho and I'm a third-year computer engineering major. This is my third year as part of AUVSI, and this year I was the software team co-lead. During competition, I will be operating the ground control station.
Hi, my name is Otto Yurch. I'm a third-year computer science major. This is my third year as a part of AUVSI, and I'm a software team co-lead. At competition, I will be operating the ground control station.
Hi, my name is An. I am a first-year computer science major. This is my first year at AUVSI, and I was in the software team. During the competition, I will be part of the flight line.
Hello, my name is Brittany Nguyen, and I'm a second-year electrical engineering major. This is my second year as part of the team, and I am the embedded co-lead. In competition, I will be part of the flight line.
Hi, my name is Justin Sun, and I am a second-year electrical engineering major. This is my second year as part of AUVSI, and this year I was the embedded co-lead. During the competition, I will be monitoring the ground control station.
Hi, my name is Jessica Chan. I'm a second-year structural engineering major. This is my second year on the AUVSI team. This year, I was the airframe co-lead. During competition, I'll be part of the flight line.
My name is Brad Sexton. I am a first-year transfer structural engineering major. This is my first year part of AUVSI. This year, I am part of the airframe team. During competition, I will be part of the flight line.
The Volantex Ranger EX was chosen as a flight platform because of the large payload capacity. The Ranger is a fixed, high-wing design with a 79-inch wingspan. A pusher-prop configuration flight platform was chosen to eliminate the possibility of a prop strike during takeoff and landing.
The fuselage was modified to fit the payload by adding a carbon fiber reinforced platform to hold the battery securely during flight. In addition, after cutting slots for the battery platform and the camera lens hole, it was noted that the fuselage was flexing during landings. As a result, carbon fiber reinforcement was added around the area of the holes and landing gear to reinforce those areas. In addition, a nose foam skid was added to protect the camera lens upon hard landings. The water bottle drop was mounted on the landing gear in order to keep the center of gravity in the optimal position and eliminate the need to cut additional holes into the fuselage for mounting.
The Ranger can be set up in less than 10 minutes, and the service time between flights is 5 minutes. The weight of the plane, including the payload, is 13 pounds. The Ranger can fly up to 25 minutes on a fully charged battery pack. The cruise speed is 25 miles per hour, and the stall speed is 11 miles per hour. The Ranger has flown 14 flights, totaling 4 hours of flight time.
The plane uses a 1000 kV Outrunner brushless motor powering a 10-inch propeller. The motor and payload are both powered by a 4S2P 5000 mAh lithium polymer battery pack. The primary payload consists of a DSLR camera, their delivery package, and the onboard computer. Other electronics include a Pixhawk autopilot, servos, RFD900 telemetry radio, FrSky X8R RC receiver radio, and the Ubiquiti Bullet M5 Wi-Fi radio.
Our software suite can be divided into 4 parts: the path planner, the ground control station, the plane onboard computer, and the computer vision system. The path planner uses Dubin's curves to generate a path that is both obstacle-free and accomplishes mission tasks. The ground control station provides an easy-to-use front end to monitor the plane's status and the status of mission tasks. The onboard computer manages the status of the plane's payload, operates the camera, and tags images with GPS coordinates. The computer vision system uses a pre-trained MASC-R CNN model to detect and classify targets and images. We are confident that our current platform will be able to complete autonomous flight, waypoint accuracy, stationary obstacle avoidance, manual image recognition, actionable intelligence, emergent target, and air delivery. We will also attempt automatic recognition of targets. We will not be attempting automatic takeoff, automatic landing, moving obstacle avoidance, or off-axis target. This year, we spent a lot more effort on unit testing our software. For example, in the path planner, each function that was used to generate a path was unit tested. This helps to catch bugs and guarantees software reliability. To consistently run tests, we set up continuous integration with Travis CI. Continuous integration runs a suite of unit tests every time someone pushes code to GitHub, and prevents code that fails unit tests from being merged into our main code base. In order to ensure that sufficient unit tests are written, any merge into our main code base has to be approved by one of the senior software members, which ensures that the new code is properly tested.
Waypoint accuracy is based on a number of factors, including wind obstacle positioning and tuning. To gather waypoint accuracy data, we gathered autonomous mission flight data over a total of 8 test flights.
Over these test flights, we hit 115 waypoints out of 148 attempted, which is a 68.8% hit rate. Totaling all of the missions that we tried, the waypoint accuracy score was 58.6 out of 123 max possible points, which is a proportional score of 47.2%. Our overall flight average minimum distance per waypoint was 86.4 feet. Of these 8 test flights, 3 were full mission tests. Over these full mission test flights, we hit 70 waypoints out of 91 attempted, which is a 79% hit rate. Totaling these full missions, the waypoint accuracy score was 44.1 out of 91 max possible points, which is a proportional score of 49.1%. The overall flight average minimum distance per waypoint for these full mission tests was 66.3 feet. Before testing waypoint accuracy, one of the most crucial elements to ensure the safety and accuracy of autonomous flight was tuning. To tune the plane, we had our safety pilot fly in various flight modes, including manual stabilize and fly-by-wire A, while performing a variety of throttle, aileron, elevator, and rudder combinations to gather data for optimizing our tuning parameters. For our tuning procedure, we went through 3 phases of tuning: roll, pitch, yaw controller tuning, navigation tuning, and TECS tuning. For testing waypoint accuracy, we tried out various configurations of waypoints, starting from basic shapes such as a square to more varied mission setups that are closer to real competition scenarios. Additionally, we tested our mission flights with static obstacles, which made the operational accuracy and reliability of our path planner critical to waypoint accuracy.
Over a total of 8 test flights, we had an average of 7.57 minutes of manual time per flight. All of these test flights included in-flight tests and tuning procedures that required manual control. 3 of these 8 test flights included full missions, which had a manual flight time of 3.9 minutes per flight. To tune our plane, we have 3 stages of tuning: roll, pitch, and yaw controller tuning, navigation tuning, and TCS tuning. To tune the roll and pitch controllers, we took advantage of ArduPilot's auto-tune flight mode, which automatically tunes the PID values based on the response time to repeated roll and pitch requests. To ensure that the plane makes sufficiently tight turns, we tuned the navigation controller. We had the plane fly a mission that was just 4 waypoints in a box and adjusted the waypoint radius parameter based on the speed and overshoot of the turns. Finally, in order to properly tune the height controller, we performed TCS tuning. This involved observing the airspeed and pitch as the plane ascends and descends. We then update the min and max pitch based on the variance of the airspeed. To make the tuning process easier, we built an application that visualized in-flight autopilot variables such as GPS location, airspeed, roll, pitch, and yaw, both during flight and post-flight. In order to test the path planner, we developed a program to randomly generate obstacle configurations, and then another program to display obstacles in the path. After visualizing tests with thousands of different configurations, we determined that the path planner struggled to generate an obstacle-free path if the obstacles were too close to the start and end points. We were able to mitigate this by adjusting the heading of the plane at each waypoint so that the plane faces away from the closest obstacle. Overall, we have found that 66% of the time we were able to create an obstacle-free path. To achieve maximum image quality, we use quantitative and qualitative methods to determine the most optimal camera settings and imaging altitude. Our first step was to calculate the expected resolution, area covered, image overlap, and motion blur based on our camera and lens specs, altitude, and cruise speed. We then took pictures from the top of a tall building on our campus to quickly iterate on parameters such as ISO, aperture, and focus until we were satisfied with image quality. Finally, we verified both our calculations and our image quality in flight. After these tests, we found that we were able to get a resolution of 36 pixels per feet, giving us at least 1,296 pixels for a 1 foot by 1 foot target. Our computer vision system is a 2-step process. The first step is saliency, which uses faster RCNN to locate and then crop out targets from full-sized images. In tests on 293 images containing 136 targets from last year's competition and our own test flights, saliency had a precision of 90% and a recall of 33%. The cropped images generated by the saliency algorithm are then sent to computers on the ground for attribute recognition. On the same dataset of 136 competition and test flight targets, we correctly classify 74% of the target's shapes, 24.3% of the target's alphanumeric characters, 52.7% of the target's background colors, and 42.3% of the target's character colors. To determine the optimal airdrop design, we used 3D printing to rapidly prototype different designs until our drop mechanism kept the water bottle secure in flight but would reliably drop the water bottle when prompted. After the drop design was finalized, we experimented with different drop altitudes, drop distances, and distance measurements. To understand the airdrop's performance, we created a simple tool to compare the release point of the water bottle with its landing point. Here, blue is where we released the airdrop, yellow is where it landed, and red is the target point. And we can see that we are overshooting the target point and need to drop at a lower altitude or from further away. Over 10 successful drops, we found that we had an average airdrop distance of 46.3 feet with a minimum of 15.6 feet. We were able to perform 3 full mission tests in preparation for the competition this year. These mission tests involved all aspects of the competition that we intend to complete, including air delivery, waypoint capture, and manual target capture. In order to accurately model the full mission test, we made sure to create a search area and waypoint path that was of similar distance and size as the one used at last year's competition. During our full mission test, we uncovered a couple of problems with our system. In our first test, we had a worse than expected localization error. This was because our localization algorithm was a holdover from last year where we had a larger plane that was able to carry a gimbal that forced the camera to always be facing straight down. We were able to improve our localization error by adjusting our localization algorithm to take into account the orientation of the plane. In addition, we found that the plane struggled to accurately hit waypoints involving a climb or descent. We plan on fixing this by improving our TECS tuning so that the autopilot has better height control. Over the course of our full mission test, we had an average score of 55.72. We avoided 13 out of 15 static obstacles, captured all of the waypoints, had 3 successful airdrops, and captured 9 out of 20 targets with 1 successful actionable intelligence run. We expect that we can improve our overall score by accounting for pitch and roll in our target localization algorithm and increasing our waypoint accuracy through more thorough TECS tuning.